Good morning. We get to an important lesson today, not just for this class, but for life in general. So some of these concepts we talk about in this class are very useful as general knowledge in our lives. So the concept of an expected value of a probability of a probability space or an experiment, if you want, is very important because it will allow you to figure out whether you should make some decisions or not, depending on your goal in life. If you talk about random events for which there is a certain payoff or loss, because if you think about it, when you talk about probabilities, if there is not a cost or a prize for random events, things will not be that interesting, right? I mean, if you go to a casino and you want to play a game, just the probability of getting, for example, let's say, the red color at the roulette or whatever game of luck you want to play at the casino, if that's the extent of it, then that's nothing, right? But we know there are payoffs associated with these outcomes. So we know that if something comes up, we're going to win a certain amount of money, or otherwise we lose. And outside, of course, of a casino, stock markets, investing instruments, many things have certain uncertainties associated with them, and of course, a certain payoff if things happen in a certain way. So this basically leads to the concept of the expected value. You shouldn't rush this section at all. I'm going to illustrate the main concept with an example first before we define it rigorously. And it's extremely important to understand what we're trying to actually figure out before we actually write down the definition of what we mean by the expected value of an experiment. So let's start with a basic example. Remember, we have two default examples that we play with when we introduce these notions because they are easy to follow: tossing the coin or rolling a die. So let's imagine a certain the following game related to tossing a coin. So let's say the provider or the organizer of the game gives you the opportunity or allows you to toss a coin repeatedly. And then the game is as follows. If the coin lands heads, then you win $2. If the coin lands tails, then you lose $1. So basically, if you want to write this schematically, with each toss, there are two things. One of the two things can happen. Heads, in that case, you win $2. So we're gonna write this as plus $2. Tails, you're gonna lose $1. Each of these outcomes has a certain probability because remember, if this is a fair coin, the probability of heads is 1/2. The probability of tails is 1/2 as well. So what could we mean by the concept of the expected value? Well, let's postpone that word for a minute, and let's imagine that we play this game 10 times. Okay, so we can illustrate this with let's see, I'm trying to figure out if I should write it by column or by let's just write it in a row. So let's say game 1, so the first game, you end up with let's see, heads, tails, heads, tails 2 times, heads 2 times, tail, and then another head. Let me see if I counted correctly, right? Because I said I played the game 10 times, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say in game number 2, we ended up with, let's say we're a little bit less lucky, because notice here we have plenty of heads, and we know that the heads is associated with a winning, not a loss. So let's say in another situation we have heads, tails twice, followed by heads, and then tail 3 times in a row, heads, heads, and another tail. All right, so what do we get? Do we win or do we lose, right? So in game number 1, remember for each heads we get $2, so I have +2 and then tail, so followed by -1, +2 twice, -1, -1, +2 twice, -1, plus another 2. So let's see how we can compute this quickly. Let's actually add all the 2's. So 1, 2, 3, 4, 5, 6. 6 times 2. And then subtract 1, 1, 2, 3, 4. So 12 minus 4. We're going to win $8. And then in game number 2, let's see, we add 2 for the heads, and then followed by 2 negative 1's, and then +2, -1 3 times, +2 twice, and then -1. So we have how many 2's? 1, 2, 3, 4, 8 2's, 1, 2, 3, 4, 5, 6, -6 times 1, that's going to be $2. So you may notice that in this type of game, so let's actually write a remark here. Even before we talk about what the expected value is, I think you could realize that this is a game that you would rather play repeatedly. Because even though the heads and tails have equal probability, you have more to gain if you end up with heads than what you have to lose. So heads and tails are 50-50 probabilities, but with each toss, the gain, the possible gain, is greater than the possible loss. So that's the reason that if you play this game a lot of times, you end up coming ahead. It's not guaranteed, so it's important to notice something important here. It's not guaranteed, so let's actually put here another example. Game 3, let's say you end up with tails, tails, heads, tails, 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 heads, and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a very unlucky situation if you think about. In this game, if you end up with so many tails and only 2 heads, obviously what you get in the end is $2 for the 2 heads, so 2 times 2, and then 1, 2, 3, 4, 5, 6, 7, 8 times 1. You're going to end up actually losing $4 if you are that unlucky and you end up with so many tails. But again, if you play the game quite a lot, you come ahead because there's 50-50 probability, and you're more likely to come ahead because of the possible gain being greater than the possible loss. The notion of the expected value that we're going to introduce later makes this notion precise in the sense of how much you would expect to gain or lose if you actually play this experiment of this game or run this experiment multiple times. One way to measure this type of gain or loss in the long run is to look at the average gain or loss per instance of running the experiment. Now, in this example of mine, we tossed it 10 times. So in games 1, 2, and 3, we toss the coin. We toss the coin 10 times. So in game number 1, the average gain or loss, right? Let's put it this way. So the average gain or loss was 8 over 10. So we played the game 10 times, we ended up with $8. So per each game, we ended up with 0.8. In game number 2, the average gain or loss, it was again still, was 2 over 10. We were kind of less lucky because we had lots of tails, was 0.2. And you could think of game number 3 as the really outlier, right? I mean, the one when you're really, really unlucky that you ended up with so many tails. And in that case, of course, per game, you actually had a loss of $0.4. But again, you're far more likely to get a positive value. And the real question is, what will be that expected positive value? So this is basically what leads to the notion of the expected value. I'm going to show you how to compute it with this example, and then we're going to define it rigorous, in a more rigorous fashion, using a clear math definition. But if you look at the first 2 examples, 0.8 is really like a lucky situation, because in that case, we ended up with lots of heads, right? I mean, we ended up with lots of heads, not too many tails. This will be kind of the unlucky situation when we had, far more, more tails than heads in game number 2. And like I said, game 3 is really, really unlucky, like the outlier. But normally, you should expect the expected value to be kind of in between these 0.2 and 0.8, because those are more realistic, so to speak, right? I mean, it's what you would expect if you flip the coin or toss the coin several times, somewhere in between, right? Between being, kind of lucky with more heads, kind of unlucky with more tails, but no outliers, in other words, right? So we're not looking at, for example, having all heads and winning really lots of money, or all tails when you lose lots of money. So this expected value, which you can actually prove that it's what you get if you run the game lots of times. So if we run the game many times, and to put it more precisely, infinitely many times, which is basically a question of a limit, actually, which won't get into it right now, but you can actually take a limit and using calculus, basically, when you want to estimate this this statement in a math way, right? So if we run the game many times, the expected payoff for this game that I illustrated in this page is going to be the gain for each outcome times the probability of that outcome. And so the summation between the product between the gain, or the payoff to be more precise, and the probability of that outcome. So you're going to win $2 if you end up with heads, and the probability for heads is 1 over 2. And you're going to lose $1 with probability 1 over 2. So the expected payoff, or the expected value for this experiment, is simply the summation between the probability of each of these outcomes times the payoff for that outcome. When we say payoff, we mean either the gain or the loss. So it could be a positive or a negative number depending on the situation. So you get heads with probability 1/2. You multiply that by $2, because $2 is what you get if you toss a head. And you lose $1 if you end up with tails, which is also with probability 1/2. So if we combine these fractions, you get 2 minus 1 over 2, which is 1 over 2, and that's $0.5. So it's very important to understand that the expected value when you run this game, it's not what you actually get. Remember, this is probability theory, nothing is guaranteed, right? It's essentially what you get on average if you run the game many times, hundreds of times, for example. But it gives you a good estimation what is going to be the payoff if you actually repeat the experiment. If you play the game only once, you're not going to get 50 cents. You are going to get or $0.5. You either get $2 or you lose $1, period. The whole point of expected value is to see what happens if you actually run the experiment multiple times. So if you run it, for example, and I'm going to show you actually with Maple, so we can run some codes to see how close we get to the expected value if we play this game. If we run the experiment multiple times, then you will be very close to this value, 0.5 per game, right? Per game. So for example, if you run it 100 times this game, if you toss the coin 100 times, you should end up with an amount of money which is pretty close to 0.5 times 100, which is basically close to $50. So you should get something close to $50 if you play the game 100 times. If you play the game 1,000 times, you should expect something close to $1,000. So with that in mind, let's stay tuned for the second page when we define rigorously what the expected value is, and then we're gonna continue with some other examples. Okay, so let's define the expected value in a rigorous way, the way it's defined in a probability theory. So suppose we have a sample space S. Remember, the sample space is the totality of outcomes of an experiment. And then suppose we also have, so let's consider a partition. I'm going to define that immediately. A partition of events A1, A2, up to AN. So the partition of events, remember, events are subsets of the outcomes. Partition means that the union of all these events gives you the whole sample space, and any two are mutually exclusive. So that means AI and AJ is the empty set. So there is no, so for any, or I and J are just indexes from 1 to n. So mutually exclusive. But the union, it means everything. We're going to show an example immediately, right? So the union of all these events is the whole sample space, and any two of them are mutually exclusive. And suppose we also have, let's suppose that the probability of A1 is equal to P1, the probability of A2 is equal to P2, and the probability of AN is equal to Pn. And A1 has a payoff equal to M1, A2 has a payoff equal to M2, AN has a payoff equal to MN, let's say. Payoff, remember, means what you gain or lose, right? So the payoffs, let's put here in the parentheses, are real numbers. Could be both positive, that'll be basically a gain for that event, or negative, or even zero. In that case, you would have a loss. So in other words, each event is associated with with a payoff. Okay, each event has its own probability, and then also a payoff, positive or negative. You can think in terms of dollars. It doesn't have to be dollars, but this is the easiest way to associate what goes on here. So then the expected value of this experiment is P1 times M1 plus P2 times M2 plus dot 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 Pn times Mn. This definition is basically fancier than it may look initially. I mean, like it's quite easy to memorize if you want to. It's just the summation of probabilities and the corresponding payoff. But I want to illustrate how this definition follows from the example we had before. So on the previous page, remember the experiment was tossing a coin, right? So the sample space in the previous example was heads and tails. The events in question were also heads and tails. So there are two events, either you get heads or tails, which form a partition. So notice that the union of them gives you the whole sample space, and obviously the intersection of them is the empty set. This is a simple example with two outcomes because it's not necessary to have just one outcome in each event. I'm going to show you immediately with another example with rolling a die how that works. The payoff for heads was $2, so M1 was 2 and M2 minus $1, right? The loss of $1 for tails. So then the expected value, according to the definition, would be because the probability of A1 is 1/2, the probability of A2 is 1/2 as well, is M1 P1, right? So that's going to be $2 times 1/2 plus minus $1 times 1/2, and that gives you 2 minus 1 over 2, 1 over 2, which is $0.5. You don't have to write this dollar symbol in the beginning of this. I just want to illustrate the difference between the probability and the payoff in the beginning. Later on, you just write the numbers, and you can write the dollars just at the end of the problem. So in a nutshell, this is what the expected value is. Again, the important thing is to make sure that the events are mutually exclusive and they form a partition like I mentioned here. So here's another example. Let's say you decide the game or the experiment is rolling a die. All right, so if we follow the definition, the sample space is 1, 2, 3, 4, 5, and 6. And let's suppose the game is the following. Let's say we look at 4 possible events. A equals 1 and the payoff is $3. So the game is that you win $3 if you roll a 1. Let's say B, the other event, is 2, 3. And let's say the payoff in this case is $1. The event 4, payoff is 0. Okay, so let's say you don't get anything. You don't lose or don't get anything if you roll a 4. And to make more stuff interesting, let's say event D, which is 5 and 6, the payoff, which is really a loss in this case, is minus $2. So notice, like before, that the 4 events I mentioned here are a partition of the sample space. The union of them gives you everything in the sample space, right? 1, 2, 3, 4, 5, 6. And they are also mutually exclusive, right? Meaning that no 2 events have any outcome in common. Okay, so what would you expect to get? What is the expected payoff or payoff, right, if you play this game? Well, what is the probability? First of all, let's establish the probability, right? So I mean, we'll do that in the next step, right? So it's going to be $3 times the probability of A plus $1 times the probability of B plus $0 times the probability of C, and then plus negative $2 times the probability of D. All right, so now we just have to establish the probability. So we have 3 times the probability of A, which is 1/6, right? So A is one outcome only. B is lending 2 or 3, so the probability will be 2/6. So it's going to be $1 times 2/6. The probability of C is 1/6 again, times the payoff 0. And finally, the probability of D is again 2/6. So each probability multiplied by the payoff and add up all this product. So what we end up here is 3 plus 2 minus 4/6, which is 1/6, and that's $0.16. So these are 2 basic examples of how we compute the expected value. On the next page, we're going to talk about the price of a game like this and what it means to be a fair game or not. This is another extremely important concept, again, not just for the course, but for life in general. When we compare the expected payoff with how much you actually pay to participate. So don't move too quickly to the next page, because I want to give you a little bit of introduction before we turn the page on this lecture. So we gave an example of 2 games, right? So in the first one with the coin, you stand to gain 50 cents or $0.5. In this one, if you play the rolling the die, according to these payoffs, you expect to get $0.16 on average. Now, if we actually continue the analogy with the casino, let's say I'm the organizer of these games, I'm the provider of these games, there will be a price to participate. So in other words, I'm offering you the possibility to play this game, but you have to pay for each rolling a die, for each tossing of the coin. So then the question is, what should be the price of that game? The price of the game has to be compared with the expected value. For example, in the game with the coin, which has an expected value of $0.5, if I, the casino owner, let's say, decide to charge you 20 cents or $0.2, then I stand to lose from providing that game, because each time customers play that game, on average, they're gonna win $0.5 per game. I'm gonna get just $0.2 as a price, charged to you to play that game. So it stands the reason that whoever provides the game, like the casino owner, stands the reason that the price of participation must be greater than the expected value. And you can bet it's going to be greater than the expected value. I mean, they're not stupid, right? So, I mean, this type of math actually is well understood at the casino. You can rest assured of that. So the price of the game has to be greater than the expected value. If it's less, then they're going to lose money. So then the concept of a fair game is when there is a break-even point. So for example, if I charge you just 50 cents, if I charge you just $0.5, then we can play repeatedly. I'm not going to win nor gain anything. So it's like a waste of time, but it's still an important comparison to be made, right? I mean, if you analyze the game, is it a fair game or not? I mean, in other words, if I play it repeatedly, do I stand to lose or do I stand to gain something? If I stand to neither gain nor lose, okay, it's a fair game, so you can basically play it indefinitely. You're not in danger of accumulating a loss, for example, but neither you won't accumulate a gain on the other hand as well. Okay, so stay tuned for the next page. Okay, so let's just define what I mentioned before in terms of whether a game is fair or not. So we say that a game is fair if the price to play is equal to the expected value. If it's not equal, it's either unfair for the player or for the organizer of the game, right? So, for example, when we, to go back to that first example, if you toss a coin, you end up with $2. If you toss a tail, you lose $1. A fair price is $0.5, which is the expected value. Any deviation from this is going to be to the advantage of the player or the organizer. So for example, if price to play is $0.2, then organizer stands to lose $0.3 on average, right? The difference between the payoff and the price to pay. So again, remember, this is what you get if let's say I'm the organizer of the game, right? So this is what you're gonna get if you play the game. I'm only charging you $0.2, therefore I'm standing to lose $0.3 on average per game. On the flip side, if the price is $0.9, let's say, then organizer of the game stands to win the difference between the two, 0.9 minus 0.5, which is $0.4. So you may wonder, this is not just about the games, by the way. I mean, you will see immediately an example. The easiest, one of the easiest comparison from real life is, for instance, insurance premium. That's one of the best examples you can pull quickly to illustrate the concept. And I'm going to do that immediately. After I'm going to go over another one with rolling the die just to illustrate the concept more. But it's not about just the games, right? But the whole point is, what is your goal, right? So I mean, if you are the provider of this game, do you want to make money or do you want to break even? So for example, if the goal is to break even and just provide entertainment for free, then I have to basically charge it $0.5. So I'm going to just charge the fair price, right? The price that is equal to the expected value. I'm not going to charge anything less than that if I don't want to lose money. But if I want to make a profit, then I'm going to charge more than the expected value and probably as high as the market can sustain, right? I mean, because I'm living off the profit, right? Of the difference between the expected value and the price, right? When the price is bigger than the expected value, I'm going to live off that difference. So for example, if you are in this last situation and you play the game 1,000 times, then 1,000 multiplied by the price minus the payoff, basically it's $400, right? So you stand to get the profit of $400 just by providing this game to the player. In some cases, the expected gain could be zero. That's also possible. So let's look at let's see. Yeah, I mean, there are some questions. So let's look at this example with the rolling of the die. So suppose that you roll a fair die, and let's take two examples of a game. Let's say if you roll a 1, then the payoff is $4. If you roll a 2 or 3, the payoff is $1. And if you roll a 4, 5, or 6, the payoff is $0. And in part B, let's give another example. Let's say if you roll a 1, the payoff is $3. If you roll a 2 or 3, the payoff is $0. And if you roll a 4, 5, or 6, the payoff is minus $1. So you lose $1 in that situation. So one possible question you may see in the homework is, how much should we charge each game to be fair? So that's a question of finding the expected value. If I want the game to be fair, the charge for each game should be equal to the expected value. So in part A, probability of 1 is 1 over 6 times 4. Probability of the second event, 2 over 6 times 1. And then 3 over 6, probability of the last event, times 0. So if we add up the two, we get 4 plus 2 plus 0 over 6, that's $1. So we should charge $1 in this case. In the second example, part B of this example, probabilities are the same, but the outcomes are different. So 1 over 6 times 3, 2 over 6 times 0, plus 3 over 6 times minus 1. Notice that if you add up all these, you get $0. So this is basically a fair game as it is. We should charge nothing. It's a fair game as it is, right? We don't need to charge anything to make it fair, because the expected value is 0. Nobody gains or loses anything in the long run. Okay, but I think it's enough to talk about rolling the die and tossing a coins. Here's an example more close to real life situations when these type of questions are relevant. Let's say, and we're going to make it very simple so that it's easy to compute in this case, right? So suppose, for instance, and that's kind of far-fetched, I gotta say. Well, actually, because I look at my notes and I actually made it, it's an example about insurance companies in the health industry. And I look at one disease only, but let's make it more general. So suppose that, let's write it this way. So suppose an insurance company wants to figure out the premium, how much they should charge. And let's say, and again, this is very, very oversimplified, right? And let's say that, let's see, insurance company wants to figure out the premium. So let's say the probability, or let's say 1 in 100 people gets sick. So I'm hesitating because I wanted to mention a specific disease, but let's make it very general, right? So let's say 1 in 100 people, for the, there's more than that, but let's say in the community or the group of people they look at, 1 in 100 people get sick. And let's say that the expected cost, the expected medical bills in case of illness amount to $5,000. Okay, and so let's suppose these are the outcomes only, right? Get sick or not get sick, and if it gets sick, if the person gets sick, then the insurance is expected to pay on average $5,000 for that person. So how do you actually relate it to the game, so to speak? With this notion of a fair game. This isn't a game, obviously, but we can continue the analogy and imagine that the insurance essentially is the provider of the game, under quotation marks, obviously. The game here is that, you stand to pay something if someone actually gets sick. Now, nobody wants to get sick. This isn't like a positive outcome, but just to strictly relate it to the example we had before with the game. So we have essentially two possible events which are disjoint, right? So event one is when a person gets sick, and A2, which is essentially the complement, right? The person remains healthy. These form two mutually exclusive sets or events, right? Because a person cannot be both sick and healthy at the same time. And the data for that insurance company states that the probability of getting sick, so the probability of one event, is 1/100. And obviously the probability of not getting sick is going to be the rest of it. So this is really like tossing the coin, except that the probabilities are not even 1/2, right? The probability of getting sick is 1/100, of not getting sick is 99/100. The expected value is how much the insurance is supposed to foot the bill, right? So the expected value in this case is simply the multiplication between the payoff in case of illness. So the insurance will pay $5,000 with probability 1/100, and it will pay $0 with probability 99/100. Obviously a much higher probability of paying nothing. That's the whole point of the insurance. But in the long run, the insurance stands to pay 5,000/100, which is $50. So this is how much they expect to pay on average in the long run. And therefore, if the insurance wants to charge a fair premium, so a fair premium, let's say the insurance is a non-profit institution, the fair premium should be exactly $50. Now, of course, the insurance better have some reserves, because you can have a year or unlucky year in which lots of people get sick. So of course they will pay more than $50. But in the long run, if this data remains correct, if the probability of getting sick is 1/100, then a fair price to charge is $50. They will charge obviously more than that, because they have to make a profit if they're in the private insurance business. This is a very, very unrealistic example, because it's very simplified, so to speak. But this is the essence of the whole premiums and charges in the insurance, right? I mean, it's basically an expected value depending on the probabilities of certain things to happen, and the payoff in this case is how much the insurance company is expected to pay in that event. So of course there are more complicated formulas. Probabilities of people getting sick varies depending on the illness, other demographic data, and so on and so forth. We're going to finish with one more page with other examples. And I think I'm going to show you one interesting example. Actually, I'm going to point out to a different video with an interesting example about switching envelopes, which I did in another video. So stay tuned for the last page. All right, so let's look at another example. So suppose that we want to organize a raffle selling 1,000 tickets, let's say for raising some funds for a cause or whatever. And then we want to figure out the price for each ticket. That'll be the question, right? So now this raffle, we have the following prices. We're going to have one first prize, $100, and let's say we want three second prizes of $50 each. So how much do we price each ticket for the raffle to be, for the price to be fair, basically? So we want to look at the fair price And also we want to see maybe how much we want to raise if you want to actually get some money. So we'll get to that immediately. So what are the events in this case? So in this raffle, right, one participant basically pulls one ticket from the basket from these 1,000 tickets. So the number of outcomes is 1,000, right? So the sample space has 1,000 tickets. There are two events of relevance here, because by the way, events with zero payoff, in this context of expected value don't matter as much, right? So we have A1, the winning ticket, so the first prize ticket. The second event, the second prize ticket. There's three of them, remember, in the basket. And A3, worthless ticket or a losing ticket. This covers everything, right? So if I take the union again of all these three events, that's the full sample space of 1,000 tickets. So obviously, because there is only a single first prize ticket, the probability of A1 is going to be 1 over 1,000. And the probability of A2, because we have three second prize tickets, that's going to be 3 over 1,000. Just to illustrate the whole concept, although this will not have any bearing in the expected value, A3, the losing ticket, are the remaining tickets, right? So one first prize, 3 second prizes, up to 1,000, there are 996 tickets which are worthless. So the expected value in this case is going to be $100 times the probability for that event, 1 over 1,000. Then it's $50 times the probability, 3 over 1,000, plus nothing, $0 times the probability for that to happen. This is 1,000 here, sorry. So, I mean, if you know what you're doing, you don't have to actually add this last term, but I just want to illustrate how it follows from the definition of the expected value, right? Because you have all the partition in the summation there. So we have, what do we have? We have 100 plus 150 over 1,000. That makes it $0.25. Okay, so the fair price is $0.25. Now, on the other hand, if we want to make sure we raise some money, we can make the price bigger than that. So let's say the price of the ticket is $1. Then then the organizer of the raffle will get on average the price they charge for the ticket minus the expected payoff. They expect to pay off 25 cents on average times 1,000 tickets. So that's going to be 0.75 times 1,000, $750. So if I want to make sure, or if I want to increase my chances to actually win something close to $750, then I should charge $1 and then subtract the expected payoff, and then that's how much I would expect to win. Again, you could win far more than that if nobody actually draws the winning tickets, neither the first nor the second winning ticket, then you get $1,000. If you're unlucky that all the winning tickets are extracted, so basically the worst situation for the organizer of the raffle is that all the winning tickets are drawn. So you have $100 for the first prize plus $150. Well, actually, yeah, that's going to be basically the worst situation with $750. So because you cannot get lower than that, right? Since you have 100 Yeah, so that's actually the worst possible situation. And of course, if you want to get more than that, you should charge obviously more than $1. So here's another example, this time from let's say business planning. So suppose, for example, that, let's say this is another example. So suppose that you have an investment account, and you want to invest equally in two companies, A and B. So the expected return for A, let's say, is 10%, and for B, let's say, is 15%. Okay, so then one question is, what is the expected return if, in this case, right, if you want to invest equally in these two companies? So you can translate this in terms of the expected value by computing the expected value of, thinking in terms of probabilities of investing in either A or B. So if you want to invest equally, that means you're equally likely to invest in A or B. So the probability of investing in A is 1/2, with the payoff in this case being 10%. So let's write that as a fraction, 0.1, plus the probability of investing in the other company, which is 1/2, with the probability of 0.15, with the return of 0.15. So you can translate this in the language of probability by looking at this keyword, investing equally, right? So thinking in terms of you're equally likely to invest in either A or B. And so the returns are different. So therefore the expected return in this case, if you compute this quantity, will be 0.125. So your expected return is 12.5% if you invest equally. You don't have to invest equally. So for example, let's say you want to invest 20% in A. So what if we invest 20% in A and 80% in the other company B? What will be the outcome, expected outcome in that case? So in terms of probability, it's like the probability of investing in A is 0.2 times the payoff, 0.1. And the probability of investing in B is 0.8 times the outcome, the payoff in that company, 0.15. Let me actually look at A, because I didn't do that before. Let's look quickly at calculator. Which I didn't have it in front of me. I should have had it in front of me before. So 0.2 times 0.1 plus 0.8 times 0.15. Okay, so that's going to be 0.14 return. All right, so I think these are enough examples. There will be an extra part at the end of this presentation. I want to run some of these examples with Maple. So you should watch that part as well. And I think that's it for today.